Curvilinear motion, normal and tangential component. If we have an idea of the path of a vehicle, it's often convenient to analyze the motion using tangential and normal components, sometimes called path coordinate. Generally, in this method, we specify the position of a point by a coordinate measure along its path and express the velocity and acceleration in terms of their components, tangential and normal to the path. Normal and tangential components are particularly useful when a point moves along a circular path. Furthermore, they give us unique insight into the character of the velocity and acceleration in curvilinear motion. What is ET and EN? They are unit vector. The unit vector ET, or the tangential direction, is tangent to the path of the particle. The velocity vector of a particle is in this direction. The normal direction, or EN, is perpendicular to ET and points toward the inside the curve. These are the equation of velocity and acceleration in terms of normal and tangential components. As we can see, the acceleration have component in both EN and ET direction, while the velocity has component only in ET direction. In the next slide, I'm going to talk about how we find velocity and acceleration with the mathematical procedure. This is only to show you how we find this equation for V and A. Consider a point P moving along a plane curvilinear path relative to some reference frame. The position vector R specifies the position of P relative to the reference point O. At the coordinate S, measures PS position along the path relative to a point O prime on the path. The velocity of P relative to O is dr dt, or delta R over delta T, when delta T approaches to the zero. Delta R is RT plus delta T minus RT. If denote the distance traveled along the path from T to T plus delta T by delta S, by introducing a unit vector E defined to point in the direction of delta R, we can write velocity equal delta S over delta T. When the delta T approaches to the zero, delta S delta T becomes ds dt, and E becomes a unit vector tangent to the path at the position of P at time t. So the velocity equals VET. Before I'm talking about how we find acceleration, we have to know that something. The parameter ρ is the instantaneous radius of curvature of the path. Theta is the angle between a fixed reference direction and the path. To derive the acceleration vector in tangential and normal component, we have to define the motion of particle as shown in a figure. Consider ET and ET prime are tangential unit vector for particle P at particle path at P at and P prime. When drawn with respect to the same origin, delta ET equal ET prime minus ET, and delta theta is the angle between them. So delta ET equal 2 sine delta theta over 2. And EN equal delta et over delta theta. When delta theta approach to the zero, we find En equal det over d theta. If the velocity vector expressed as a v equal vet, the particle acceleration may be written as a equal dv dt. This is the mathematical derivation procedure of acceleration. After we substitute this value to this equation, we find the acceleration. At equal dv dt and an equal v squared over rho. As we can see, the tangential component of acceleration reflects change of speed, and the normal component reflects the change of direction. The tangential component may be positive or negative, and normal components always point toward the center of the path curvature. Consider point P. If the motion occurs in the plane xy, plane of Cartesian reference frame, and theta is the angle between the x-axis and unit vector et, the unit vector et and er are related to the Cartesian unit vectors by et equal cosine theta I plus sine theta j, en equal minus sine theta I plus cosine theta j. If a point P moves in a plane circular path of radius r, the distance s is related to the angle theta by s equal r theta. Velocity equal r omega. Omega is the angular velocity. The tangential acceleration has a tangential and normal component, and we can express in terms of angular acceleration. At equal r alpha and an equal r omega 2. Okay, before to see any example, just quick review the important part of this section. The anti-coordinate system is fixed on the particle, therefore moves with the particle. When described using anti-components, the velocity only has one component, VET. Acceleration has two components, AT and AN. AT is the change in speed and AN is the change in the direction of the velocity. Therefore, we have V equal ds dt, so AT equal dv dt, AN equal V2 over rho. En, as you can see in the figure, always point to the concave side of the path. For the circular path, the instantaneous radius of curvature, rho equal r, or radius of the path. If the path is known as a y equal fx, we can find the rho with this equation. Let's look at some examples. The motorcycle starts from rest on a circular track with a 400-meter radius. The tangential component of the motorcycle's acceleration is given as a function of time, at equal this equation. What is the motorcycle velocity in terms of normal and tangential component at time 10 seconds? And what distance s has the motorcycle move along the track at time 10 seconds? Okay, Let S be the distance along the track from the initial position of the motorcycle to its position at time t. Knowing the tangential acceleration as a function of the time, we can integrate to determine the velocity and position as a function of time. Okay, integrate the tangential acceleration and find the velocity. This is the equation for velocity as a function of the time. At time 10 seconds, the velocity equals 30 meters per second. We can express the velocity in terms of tangential component at time 10 seconds. We know that the V equals VET. We substitute our result and we write the velocity as a tangential component. For finding the position, we have to integrate from the velocity. Integrate the velocity to determine the position as a function of the time and find the position at time 10 seconds. The answer is 133 meters. A motorist is traveling on a curved section of highway of radius 2,500 feet at a speed of 60 miles per hour. The motorist suddenly applied the brakes, causing the automobile to slow down at a constant rate. Knowing that after 8 seconds the speed has been reduced to 45 miles per hour, determine the acceleration of the automobile immediately after the brakes have been applied. First of all, we have to define our coordinate system. In this example, we use the normal and tangential coordinate system. After that, we have to convert velocity from miles per hour to feet per second. Next step, according to the problem, the automobile has a constant deceleration. Therefore, AT equal average AT equal delta V over delta T. The answer of the average is equal minus 2.75 feet per second square. Now we have to calculate the normal acceleration. Immediately after the brake or applied the speed is still 88 feet per second. So we can find the AN equal V2 over rho. We find AN equal 3.10 feet per second. And finally, determine overall acceleration magnitude after the brake have been applied. A equal 4.14 feet per second and alpha equal 48.4 degree. Last example. During a flight in which a helicopter stops from rest, the Cartesian component of its acceleration are AX and AY. What are the normal and tangential component of the helicopter's acceleration and the instantaneous radius of curvature of its path at time 4 seconds? First, we have to write known and unknown of problem. As we can see, we have to find AT, AN, and rho at time 4 seconds. Okay. Integrate the component of acceleration with respect to the time and we find the velocity, Vx and Vy. At time equal 4 seconds, the Vx equal 4.80 and Vy equal 4.32 meters per second. For tangential unit vector ET, we can use this equation. ET equal V over magnitude of V. When we substitute the data, we find ET equal 0.743 I plus 0.669 J. After that, we can find the tangential component of acceleration at time 4 seconds. We know that AX and AY at time 4 seconds. Tangential component of the acceleration at time 4 seconds equal AT equal ET dot A. After we substitute all the data, we find AT equal 2.02 meter per second. Now we have to find the AN, but before that we have to find the magnitude of the acceleration. The magnitude of acceleration is 2.43 meter per second square. So we find AN from this equation, and AN is 1.34 meter per second. The last step is finding the radius of curvature of the path. Rho equal V2 over AN. The answer is 31.2 meter. Thank you for watching.